All right, hello y'all. So today we're going to do the chapter 7 practice test I gave you. So starting right out, which is the following constant expression for the following equation, the equilibrium constant. So starting with NO2F should be on the top. Therefore, this cannot be it. Next, it should have an exponent of 2. So our top should look like this, NO2F to the power of 2. Therefore, B and A cannot be it. Our answer is D. Do not have to look further, but just in case, you put the products on the top and the reactants on the bottom, again, with those exponents being the coefficients. So that's number one. Number two, KC4N2O gas is going to react to this equation. We know the equilibrium constant is greater than 1. What is Kc for the following reaction at the same temperature? I see that the following reaction is switched in two ways. One, this reaction is flipped. So what was once going right is now going left. That means our Kc will actually be 1 over our original 7.3 times 10 to the 34th. Another thing I notice is that we have half of our coefficients. Because we have half of our coefficients, then our square roots, because remember, if before we had uh, our N2O to the power of 2, well, because now we have less than that, we only have N2 to the coefficient of 1. If we wrote this whole thing again, it would actually be the square root. So it is going to be the square root of 7.3 times 10 to the 34th. And to work this one out, just to be a little clearer, let me go ahead and erase these. I'm going to write the original Kc. So the Kc for our original equation was Kc equaled our products, O2 times N2 to the power of 2 all over N2O to the power of 2. Our Kc for the reverse is equal to, now, N2O to the first power over O, oh, whoops, O2 to the 1/2 power and N2 to no exponent. So basically what we're looking at is the transformation. So the first thing I notice is that we do the inverse. That's how we flip it. And therefore our Kc is now, if this is our Kc initial, this is our Kc final. Oh, you know what? Let me make this clear. This is our Kc for our forward reaction. This is our Kc for our reverse reaction times a half, because half the coefficients. So our Kc forward is equal to the Kc, whoops, Kc 1/2 the reverse reaction inversed, because we had an inverse transformation between these two, and then square rooted, because I went from a 1 exponent to a 1/2 exponent. That's a square root. I went to a 2 exponent to a 1 exponent, went 2 exponent to a 1 exponent. So it really is 1 over the square root, B. All right, so for number 3, consider the following equilibrium reaction. We notice that H is greater than 1. Now, because it's greater than 1, we know it's endothermic. We also know that we have 3 moles of gas and 4 moles of gas on either side of the equilibrium. So with this said, we are going to figure out how to shift the equilibrium to the right. When we shift the equilibrium by first just looking at the gas, we know that if we want more gas, then all we have to do is decrease pressure. Because when you decrease pressure, This wants to balance out, so it will add gas particles by shifting right. If we were to decrease temperature, that can't be right because the system would then want to shift left. If it's greater than 1, it's endothermic, meaning it will absorb heat. So we don't want this system to absorb heat. If we decrease the temperature, we want to release heat, which would actually shift the equilibrium backwards. So it can't be that. Increasing this, just adding more to that, will also shift the reaction backwards. It's trying to balance the scale, so that will then go to create more of the reactants. Same as decreasing the oxygen, the NO in the product will decompose to add more oxygen. So it's A. Consider this reaction. The values of Kc at different temperatures are as follows. So we notice that Kc actually increases with temperature. So the higher the temperature, the higher the Kc, which means as we are increasing temperature, the reaction is shifting that way, meaning it's trying to absorb the heat, absorb heat of system. All right, so let's see. Which statement is correct at higher temperature? The forward reaction is favored. Definitely true. We already see that. The reverse reaction is favored. That contradicts it. The rate of reverse reaction is greater than the rate of forward reaction. Well, that can't be true because we still find an equilibrium. And if the rate of reverse reaction was greater, then we would have a lower Kc. Concentration of both reactants and products increase. That's impossible because we can't increase both concentrations at once. At equilibrium, as one moves up, the other moves down, and vice versa. All right, moving on to number 5. The equilibrium constant for this equation is K, just K. What is the equilibrium constant for this equation? Well, I notice that we are adding more exponents. We're actually doubling the exponents. And so if we think about this as exactly the same as our first equation, NH3 squared over N2 and 3H2, oops, my bad, H2 cubed, well, our new equation is going to actually change this to a 4, this to a 6, and this to a 2, which means we multiplied the exponents by 2. That means we had to square it. It's going to be C. All right, which factor does not affect the position of equilibrium in this reaction? So, change in volume. Now, change in volume doesn't affect liquids, it doesn't affect solids, but it affects gases. So if we look at this, we have 1 mole of gas, 1 mole, and 2 mole. So yeah, changing the volume would affect gases by changing concentration, and even pressure, So it can't be volume. Volume will make a change. Change in temperature. Well, we know that this reaction is exothermic, meaning if we change the temperature by increasing the temperature, this reaction will move backwards. If we decrease the temperature, this reaction will move forward, so it can't be that. Adding a catalyst. Well, catalysts don't affect equilibrium at all, so bam, already know. It's got to be C. Change in pressure is essentially the same as volume when we're dealing with gases, so can't be that. Answer C. What is the effect of increasing the temperature in this reaction? So we know that this reaction has a delta H of less than 0, which means it's exothermic. So if we change temperature, specifically increasing, when we increase temperature on an exothermic, we are shifting it backwards. Okay, that's really important to note. So as we shift it backwards from increasing temperature, we have to kind of figure out what's going to happen here. Now, with this equation, we know that H plus is acidic. So if we shift backwards, we are going to decrease H plus concentration. And if we decrease H plus concentration, that means this is going to become basic. And if it becomes basic, that means pH increases. B. All right. Number 8. What occurs when the pressure of a given equilibrium is increased at constant temperature? So we're given pretty much the same equation we have this whole time, nitrogen oxygen forming nitrogen monoxide. We're given a positive enthalpy value, meaning that this equation is endothermic. And so with this endothermic reaction, let's see, when the pressure is increased, well, what happens with pressure? We have 2 moles of gas here, 1 mole, 2 moles of gas here. Turns out, because we have the same pressure on both sides, or the same amount of moles on both sides, pressure isn't going to change anything. Kc should stay the same. The position will be unchanged. All right, moving on to number 9. What will happen if the pressure is increased in the following reaction mixture at equilibrium? So we have CO2 plus H2O turns into H plus H3O minus. And once again, we have to look at this, thinking about whether or not we have gases, whether or not we have gases because of pressure. And we got to think back to that H plus being acidic. So if we increase the pressure, we want less gas. Because we want, whoops, gas has 1s. We want less gas. And because we have 1 mole here and 0 moles on the right side, what we're actually going to do is shift the equilibrium to the right. So we already know it can't be either of those because those say left. So it's one of these two. And if it's acidic, that's a low pH, meaning that it's got to be A. Equilibrium will shift to the right and pH will decrease. All right, consider the equilibrium between N2O4 and NO2. Once again, always looking at delta H first thing. This is endothermic. Now, something to note is that it wasn't important here in this reaction, but honestly, I don't care. I always want to look at delta H right off the bat. If they give us information, I'd rather analyze it first, and maybe I don't use it, that's okay. So, 2, which changes shift the position of equilibrium to the right? Well, if I want more product on an endothermic reaction, turns out I have to, I have to increase the temperature. Whoops. Increase temperature. Because as I increase T, it will use it. It will consume it by moving forward. Okay, so it's got to be increasing temperature. Decreasing pressure, let's see. We have 1 mole here. We have 2 moles here. And so if we want to add more gases, then yeah, we'll decrease the pressure because this will try and add more gas to add pressure. And thus by doing so, we know it's 1 and 2. Oops, nope, hold up. last one, number 3, adding catalysts. Oh, well, catalysts don't change the reaction. It is 1 and 2. A, bam, got it. All right. What is the equilibrium constant expression Kc for the following reaction? All right, we can all do this by now. Kc is equal to the top, N2O, no exponent. H2O, exponent of 3. Let's see if any of these have this. Not that one. Not that one. Not that one. Oh, I don't even have to finish. It's got to be D. That's it. Straight and simple. With Kc, you can eliminate almost all the options just by doing the top. All right. The enthalpy change for the dissolution, dissolving of NH4NO3. So we're assuming this reaction is this turning into its byproducts, into NH4 plus NO3 minus. So that is our forward-backwards reaction, is positive. Which statement about this reaction is correct? And we get a little hint. Solubility refers to the dissolution equation, which is what I drew right up here. So the reaction is exothermic. Well, we know this reaction's endothermic, so A and B are automatically impossible choices. All right, so the reaction is endothermic and the solubility decreases at higher temperature, or the reaction is endothermic and the solubility increases at higher temperature. Well, as an endothermic reaction, as we increase the temperature, it is more likely to progress. Therefore, the solubility increases because solubility means dissolve, which is exactly what's happening here. All right, moving on to number 13. Which variable affects equilibrium constant Kc? Now, this one's a little bit tough, but we definitely can eliminate some right away. Catalyst is gone. Atmospheric pressure may not be the pressure that we're doing our reaction at. We can be doing our reaction in a pressure chamber. The Haber process does its reaction in a chamber where they can control the pressures. So who cares about the atmosphere? And then we're stuck between these last two. But one of these answers is completely incorrect, or not just, it's not incorrect, it's incomplete. And that's this one. We need concentration of reactants plus products. We need both. And as we change those concentrations, the equilibrium will shift anyways. So the concentration of reactants and the products don't necessarily change the equilibrium constant, because the equilibrium constant is a thing that exists. And so as we add more reactants, then it'll turn into products. And once it reaches equilibrium, the overall Kc is going to be exactly the same. So it's got to be temperature. Big one. All right. So what happens when temperature of the following equilibrium system is increased? First off, like I say, let's check. It's exothermic, which means as we increase T, it will move backwards. Because with a negative 91 kilojoules, moving forwards releases that heat. So we don't want to add more heat to the system if we're already increasing the temperature. So we know that when we increase temperature, we should be moving backwards or to the left. All right, so we can automatically eliminate C and D. All right. Now, reaction rates of forward and reverse reactions. Do they increase or do they decrease? And this one gets a little bit tricky. If we increase the temperature, we know it shifts to the left. Left always seems like a decrease. But we're only shifting the equilibrium. If we think about temperature and think about collision theory, as we increase the temperature, we have more collisions. And more collisions at high temperature. And therefore, we're going to have a faster rate. Now, the forward and backwards rate are both faster, but overall, the individual rates are faster. All right. 15. The exothermic reaction I2 plus 3Cl2 reacts to form 2ICl is equilibrium in a fixed volume. What is correct about the reaction quotient Q and shift in position of equilibrium? The instant temperature is raised. All right. So we're talking about temperature, we're talking about reaction quotient. So exothermic. First things first, if temperature is raised in an exothermic reaction, it will shift left. So what happens is we know that Q was equal to Kc initially. But because the reaction is shifting left, Kc is decreasing. And therefore Q will momentarily be greater than Kc until it becomes equilibrium. So B shifts left and Q is greater than Kc. Sulfur trioxide is produced from sulfur dioxide. Outline giving a reason the effect of a catalyst on this reaction. So you all know this one. This is actually chapter 6. So a catalyst is going to feed, or sorry, let me use proper terms. Catalyst is going to increase rate forwards and backwards. Furthermore, catalysts decrease activation energy. So you can get points for that. You can also get points by saying catalysts provide alternate pathway for reaction. You can get 2 points for this, and any of those three will get you 2 points. Any two of those three will get those points. All right, moving on to 17b. The reaction between sulfur dioxide and oxygen can be carried out at different temperatures. Guess what, y'all? You have done this problem before. I wanted you to do it again because only a couple people got this right. So let's sketch our Maxwell-Boltzmann energy curves. I'm going to use blue for our lower temperature and red for our higher temperature. I'm going to throw an EA for both of these. And I'm going to label this my T2 and this my T1. All right, there's my Maxwell-Boltzmann distribution. Okay, so let's talk about this. Explain the effect of increasing the temperature on the yield of SO3. Well, if we look back at our reaction, actually we don't have a reaction, but honestly, it does not. Oh, we do have a reaction. It's up here. If we're trying to increase the yield of SO3, we have an exothermic reaction. So we should note that this reaction is exothermic, which we know, therefore, the reverse reaction is favored as temp increases. If the reverse reaction is favored as temperature increases, then you need to make sure that you mentioned that the equilibrium shifts left. And then finally, we have to talk about the yield of SO3. SO3 decreases. Or let me throw the word yield in. Yield of SO3 decreases. All right. Moving on to our good friend, the Haber process. Ammonia is produced by the Haber-Bosch process, which involves this equilibrium that we know and love. And we can even see that the percent of ammonia at equilibrium under different various conditions shown. So we see that higher temperature, or sorry, lower temperature, higher temperature, even higher temperature. So as we increase temperature, amount of ammonia we get decreases. Furthermore, as we increase pressure, ammonia increases. Did you see expression for the equilibrium constant Kc for this equation? Easy peasy. We see that NH3, we've done this one in class so many times, N2, H2, to the second, to the third, and N is fine. And that is your mark right there, real quick. Just make sure you get those easy points. All right, state how the use of catalyst affects the position of equilibrium. It doesn't. Bam. There you go. You want a mark? Say it doesn't. All right. 18C, with reference to the reaction quotient Q, explain why the percentage of yield increases as pressure is increased at a constant temperature. All right, so we are basically looking at the reaction quotient because we're saying as we increase pressure, we are constantly shifting equilibrium. So we can't be looking at the equilibrium because this is in dynamic equilibrium. It is in movement, it's changing. So we really just have to focus about yield increases as pressure is increased. Well, when we increase pressure, concentration of gas increases. That's just basic statements. We're saying we're increasing the pressure by increasing the concentration of gas, and that could come either from decreasing the reaction chamber, the volume of it, squeezing the particles closer together, or pumping more reactants in. Either way, we're going to have an increase in pressure. So we can say that. But furthermore, just by our knowledge, if we're shifting the reaction to the right, we are shifting towards ammonia. That means that during this point, when we increase pressure, whoops, when we increase pressure, in that moment, Q is actually going to be less than Kc because it tells us that we're going to be, this little statement right here tells us that we must produce more ammonia to get Q to equal Kc. So that'll get you the marks too. You need to make sure that you have these statements and your thoughts are relatively organized. And you can get all your points right here. Oh, you know what? Let's just add another simple statement that will get you points. If we're saying that yield increases as pressure increases, say pressure shifts equilibrium right. So 0.1, 0.2, 0.3, all good points. All right. Moving on to an actual paper 3 question I put on this test. I wanted you to start looking at data, which this other one was paper 3-ish, but I felt like it was kind of a nice hybrid. But now this is a real paper 3 question. An investigation was carried out to determine the effect of chain length on alcohol on the equilibrium constant Kc for this reversible reaction. And you'll notice, just if we keep it in our mind, H plus is an acid, and we do this in an acidic solution. Anyways, the reactants, products, and the catalyst form a homogeneous mixture. Fixed volumes of each alcohol, ethanoic acid, and sulfuric acid catalysts were placed in sealed conical flasks. At equilibrium, the flasks were placed in an ice bath, and samples of each flask were titrated with NaOH to determine ethanoic acid concentration present in the equilibrium mixture. The following process results were obtained, and we get this chart full of data. You'll actually notice that we have a couple things here. We have a Kc that is high at the top and it gets lower. All right, identify the independent variables of this experiment. Independent, dependent. Turns out you don't need to read any of the other stuff for this first problem. I just wanted you to start looking at things. Now they even tell us right here, fixed volumes of each alcohol, ethanoic and sulfuric acid clouds were placed in conical flasks, and you did this thing. Furthermore, they literally said that an investigation was carried out to determine the effective chain length on equilibrium constant. When you see this statement, effect of on, like the effect of temperature on evaporation, the effect of giving chocolate to my students as a source of motivation, the effect of blank on blank, the effect of this is going to be your independent variable. So your independent variable is chain length. Another little secret is it's usually the first column that's not labels. Here's our labels. But then again, these are the same exact thing. Meth means 1, eth means 2, prop means 3, but means 4, pent means 5. And we have 1, 2, 3, 4, 5. Just by logic, you can determine that chain length is our independent variable. All right, dependent variable, they literally told us the effect of on equilibrium constant. So our dependent variable is equilibrium. Equilibrium. And specifically, they say to determine ethanoic acid concentration present in the equilibrium mixture. So equilibrium concentrations. So my big hint for these ones is just read the text because honestly, the answers are there. All right, so that's our independent and dependent. All right, so this last problem. Ice bath is used at equilibrium to slow the forward and reverse reactions. Explain why adding large amounts of water to the reaction mixture would also slow down both reactions. All right, so this doesn't actually have anything to do with equilibrium. This has to do with, collision theory. So, more water, more dilute, lower concentrations, less collisions, lower rate. This is all just logical thought. Boom, 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 boom. And basically, all you have to do is think about this in terms of collision theory, and it doesn't matter which way the equilibrium shifts. We know that overall rate will slow down because we have large amount of water and we have lower concentrations due to that. The other thing you know, and the other way you know it's collision theory, is they say it's ice bath to slow down the reactions, meaning they're already talking about temperature slowing down the reactions. And in collision theory, temperature can speed or slow down, but concentration can also speed or slow down. And they already gave us one, so we're just doing the other one. With that, I hope you all will do well, and I hope this video helped.